Have you ever stood on solid ground and suddenly wondered what if the earth beneath your feet is actually alive? What secret fire is roaring deep inside our planet right now, pushing hot rock upward every single second? And how can that same terrifying power quietly create the richest soil we depend on for food? The very crowd that feeds billions of people. Pick up because today we are diving straight into the blazing heart of Earth itself. And I promise you will never look at the ground the same way again. Picture this. You are standing right where you are now. The ground feels rock solid and safe under your shoes, but just 30 to 70 kilometers straight down, that's closer than many flights you've taken in your life. Everything turns into a raging, unstoppable furnace. Our planet is like a giant, fiery onion with layer after layer of extreme heat and pressure. At its very center is the inner core, a small pool of solid iron and nickel blazing at 6,000 degrees Celsius, hotter than the surface of the sun itself. Surrounding it is the outer core, a wild, swirling ocean of liquid matter spinning so fast that it creates Earth's invisible magnetic shield that shall protect Earth every day from deadly solar winds and radiation that would otherwise try life on the surface. But the real action happens above that in the mantle, a massive 3,000 kilometer thick layer that makes up a gaping 84% of our entire planet. The rock here isn't fully melted like lava in a volcano. It's a superheated, slowly churning plastic like soup, flowing like thick, glowing honey over millions of years. The endless, powerful dance is called convection. Hot rock rises, cooler rock sinks over and over again, just like water boiling and rolling in a pot on the kitchen stove. That movement never stops because of the insane heat trapped inside. So where do all the incense non-stop heat actually come from? Let me break it down for you with three powerful sources that keep our planet cooking 24 hours a day, 7 days a week. First, there's leftover fire from Earth's wild and chaotic purge 4.5 billion years ago. Back then, giant asteroids and rocks slammed into each other in a cosmic smash up so massive that the whole planet became a glowing ball of molten lava. Some of that original heat is still trapped deep inside. Second, and there is the real superstar that powers most of the soul as radioactive decay. Tiny atoms of uranium, thorium, and potassium deep inside the rocks, slowly breaking apart like tiny nuclear reactors, releasing heat non-stop, powering 60 to 80% of Earth. There is no furnace. Third, the moon and sun tug on our planet with invisible gravitational hands, creating tidal friction that adds even more warmth, like gentle but constant message from space. That non-stop heat is the engine that drives absolutely everything on our dynamic planet. It powers the mantle's massive convection currents, which shove huge slabs of Earth's outer shell, called tectonic plates, across the surface at a few centimeters below. The plates are like giant puzzle pieces floating on a sea of fire beneath them. When they pull apart, smash together, or grind past each other with incredible force, something magical and dangerous happens. Magma is born. Magma, that glowing molten rock that will soon become lava on the surface, is literally the blood of our living, breathing planet. Here's the mind-blowing part that still amazes scientists today. Volcanoes don't just pop up anywhere on Earth. They love three very special hotspots where the action is always happening. First, divergent powers where plates rip apart like two people pulling a piece of bread in half. Imagine the middle of the Atlantic Ocean, a massive crack in the sea floor called the mid-ocean ridge that stretches for thousands of kilometers. Here, pressure drops dramatically, mantle rock melts into runny pulsed magma, and brand new ocean floor is born every single day. Island sits right on top of the tearing sand, so the island is literally splitting open and growing bigger while people live their normal lives there, driving on roads that sometimes crack open with steam coming out. Second, conversion powers where one plate dies under another in a dramatic, violent process called subduction. The sinking plate drags water-rich rocks down into the extreme heat, that water acts like a secret magic ingredient, lowering the melting point of the rock, exactly like sprinkling salt on ice to make it melt faster on a hot day. The result, thick, gas-backed magma that builds some of the world's most dangerous and beautiful volcanoes. Welcome to the Ring of Fire around the Pacific Ocean, home to 75% of all active volcanoes on Earth, and some of the most explosive eruptions in history. And third, hotspots. Sandpipes are super hot rock shooting straight up from deep in the mountain, completely ignoring the place moving above them. Hawaii is the superstar example that everyone knows. The Pacific Plate drifts slowly over a fixed hot plume, creating an island chain one by one over millions of years. And right here in Vietnam, we have our own ancient hotspot volcanoes in the Central Highlands, places like Chudong that erupted millions of years ago and left behind that famous rich red basalt soil you see covering the hills and farms today. Scientists finally cracked the entire mystery in the 1960s with the revolutionary theory of plate tectonics. It all started when Alfred Wegener noticed back in 1912 that the continents fit together like giant puzzle pieces, but nobody believed him at first. It took Harry Hess and many other brilliant minds to prove that. The ocean floor itself was spreading like a giant conveyor belt. Today we use satellites and GPS technology to track every tiny movement in real time, watching the place move just like scientists predicted. Magma itself is no simple liquid you can pour like water. It's a wild, complex mix of melted rock, floating crystals, and dissolved gases all trapped under enormous pressure. It forms 50 to 200 kilometers down where the heat and pressure hit the perfect sweet spot for partial melting. Different kinds of magma act completely differently because of one key ingredient, silica content. Low silica basalt magma is thin and runny like warm honey, flowing easily and creating gentle eruptions. High silica rhyolite magma is thick and sticky like peanut butter, trapping gases and building up pressure for massive explosion. Andesite magma sits right in the middle, the most common trouble marker you'll find all around the Ring of Fire. Now you truly understand how volcanoes are born from Earth's inner fire The same incredible heat that once forced our entire planet billions of years ago is still hard at work right now, deep below Earth. But here's the real questions that the properly burning in your mind right now. How does the magma actually travel upward to the hundreds of kilometers of solid rock without melting everything in its path? What decides whether a volcano will be gentle and beautiful like a Hawaiian lava flow and or explosive and terrifying like a Plinian blast? The thrilling dramatic answer is coming right up in part 2. Don't go anywhere. What exactly is this glowing, fiery liquid we call magma? How on earth do it manage to climb to hundreds of kilometers of solid rock without destroying everything about it? And why do some volcanoes rise like Zanto white shows while others tower like airy giants ready to explode at any moment? Come with me now. We're going deep inside the secret hidden world of magma, and I guarantee you'll be amazed at every step. Magma isn't just melted rock sitting quietly underground as a bubbling, living soup made of liquid stone, millions of tiny crystals floating around, and explosive gases like water vapor, carbon dioxide, and sulfur dioxide all trapped under insane pressure. It forms when mantle rock finally has 1100 to 1300 degrees Celsius, and the pressure drops low enough for only 5 to 20% of the rock to melt. Think of it exactly like chocolate chips slowly melting inside a warm cookie in the oven. Not everything turns liquid at once, just enough to let the whole thing start flowing, moving. There are 3 dramatic and very different ways magma is created, and each one tells its own exciting story. Decompression melting happens when tectonic plates pull apart and the pressure suddenly drops, exactly like cracking open a shaken soda bottle. So all the bubbles explode out at once. Flux melting strikes hard at subduction zones when water from the sinking plate sneaks down into the hot metal and acts like a magic melting potion, lowering the temperature needed to create magma. And hotspot melting, that's pure, unstoppable heat blasting straight up from the deepest parts of the mantle like a sand underground plow thought. Once magma is born, it becomes lighter than the solid rock all around it, so it begins its long, slow, and sometimes dramatic journey upward toward the surface. It doesn't just plunge a straight tunnel like a rocket. Instead is next to tiny cracks and weaknesses in the crust, squeezing into vertical walls called dikes and flat sheets called shears. Along the way, magma changes its personality in fascinating ways. It mixes wet melted crust rock in a process scientists call assimilation, or it drops heavy crystals that sink like stones in a river, a process called fractional destabilization. All the changes make the magma thicker, richer in gas, and far more dangerous the closer it gets to the surface. Eventually, the magma collects and pools in giant underground reservoirs called magma chambers, usually sitting 5 to 20 kilometers below the surface. Here the pressure really starts to build like a pressure cooker on the stove. Gases that were happily dissolved under high pressure now start forming bubbles, just like when you shake a soda bottle hot and then open it. If the magma is running past, the bubbles escape easily and you get stunning, beautiful lava fountains shooting into the sky. But if the magma is sticky, ray or light, the bubbles stay trapped. Pressure skyrockets higher and higher, and the whole chamber becomes a ticking time bomb ready to blow. That single difference in how thick or runny the magma is creates 3 legendary and very different volcano shapes that you can see all over the world. Sheer volcanoes spread out wide along with gentle slopes, looking exactly like warriors shield on the ground, because their thin basalt lava races for many kilometers across the land before it cools. Mount Laurel in Hawaii is actually the tallest mountain on Earth when you measure it from the ocean floor all the way to the top. Over 10 kilometers high, stratovolcanoes, also called composite volcanoes, are the steep, dramatic, and often perfectly cone-shaped ones built layer by layer with alternating flows of lava, ash, and rock fragments. Think of the iconic perfect cone of Mount Fuji in Japan, or the protein dangerous Mount Vesuvius in Italy that everyone still talks about. Cinder cones are the quick and smaller ones, simple, steep cones made entirely from exploded pieces of lava and rock that pile up fast around the vent. Right here in Vietnam, Chulanda stands as the perfect example of an ancient cinder cone that has been sleeping for millions of years. Its old lava rivers cooled and turned into the famous red pasture soil that covers the Central Highlands. Farmers today grow some of the world's best coffee on that rich soil, a real gift from the volcanoes of the past that still feeds families and brings money into the country every single day. Modern science has given Earth incredible tools to spy on magma like never before in human history. Seismologists listen carefully to the tiny earthquakes it causes as it forces its way upward. Satellites reporting high above what the ground swell and bird using advanced answer technology get sensors placed near vents sniff for sulfur dioxide and other warning gases leaking out. All the tools together give scientists precious days or even weeks to warn people before big eruption, saving thousands of lives. Viscosity, that's scientific word for how thick or runny the magma is, decides the entire personality of a volcano. Low viscosity means smooth, beautiful, and relatively safe flows of lava. High viscosity means gases get trapped and violent explosions become almost guaranteed. Add more dissolved gas into the mix and the tremor multiples 10 times over. Scientists study every single detail of the processes every single day to keep millions of people living near volcanoes as safe as possible. But the true fireworks, the real show that everyone remembers, begins the exact moment magma finally breaks through to the surface. What turns on that silent underground pressure into one of nature's most spectacular and sometimes terrifying performances. Why do some eruptions create peaceful rivers of glowing fire while others unleash deadly clouds racing down mountains at terrifying speed? And how can one single volcanic blast actually change the weather across the entire planet for years? The explosive heart pounding as explodes in part 3. You won't want to miss it. And what suddenly turns quiet hidden magma into one of nature's most violent and breathtaking performances? Why do some eruptions paint the landscape with beautiful rivers of glowing fire while others unleash deadly clouds of death racing down mountains at highway speeds? And how can one single explosion actually change the weather for the whole planet and affect millions of people far away? Get ready. There is the dramatic moment when Earth's inner head finally breaks free in the most spectacular way possible. An eruption starts deep down. When the pressure inside the magma chamber becomes completely unstable, as the magma rises up the final few kilometers toward the surface, the pressure drops like a rocket launching into space. Although trapped gases expand thousands of times in a split second, turning the magma into a foaming 40 meter ready to explode. In running past some magma, the foam breaks gently and beautifully, like not shooting joggers. Hawaiian style fountains of lava, hundreds of meters straight into the sky, like natural fireworks. But in sticky high viscosity magma, the foam stays trapped like a cork in a bottle. Pressure builds and builds until the rock above literally shatters in a massive, shaking explosion. Scientists have clear names for every single style of eruption so they can predict and understand them better. Hawaiian eruptions are effusive and relatively peaceful. They produce long flowing rivers of lava that move slowly enough for people to watch safely from a distance. Strombolian eruptions fire lava bombs and glowing fragments in rhythmic bursts, almost like a fireworks show that happens every few minutes. Volcanic eruptions are sudden, loud, and very violent, sending ash and rocks high into the air without much warning. Plinian eruptions are the true monsters of the volcano world. They create towering columns of large ash and gas, soaring 20 to 50 kilometers high into the stratosphere, exactly like the famous 79 ID plus of Mount Vesuvius that buried the ancient city of Pompeii in hot ash and preserved it perfectly for thousands of years. Plinian eruptions are the deadliest of all. They send super-hot pyroclastic flows pouring down the slopes at 700 kilometers per hour, incinerating everything in their path like a deadly avalanche of fire and gas. History is absolutely packed with jaw-dropping, unforgettable moments that changed the world. In 1883, the island volcano of Krakatau in Indonesia exploded with such insane force that the sound were heard for 1,600 kilometers away. People thought it was cannot fly from distant worlds. The dust and ash blocked the sun for years and created beautiful red sunsets all around the world clock. Tempora in 1815 was even bigger and more destructive. As eruptions trickled the year without a summer, in 1816 causing massive crop failures, famine, and even social unrest across Europe and North America. Mount Benetbro in 1991 held 20 million tons of sulfur dioxide high into the atmosphere, cooling the entire planet by half a degree Celsius for 2 full years and affecting weather patterns worldwide. Even in our modern world, more than 800 million people still live within 100 kilometers of an active volcano, but science has given Earth real powers to fight back, seismographs detect the smallest warning tremors, deep underground gas monitors sniff out danger changes in the air, and satellites track every tiny part and movement in the ground. In 1991, thanks to the amazing tools working together, thousands of people were safely evacuated from the danger zone around Pinatubo just in time before a giant blast. Every single eruption, whether big or small, as a dramatic and powerful reminder of how alive and active our planet truly is. After the rock finally fades and the ash slowly settles back to the ground, can something truly beautiful and life-giving actually rise from all that destruction? How do volcanoes, famous around the world for wiping things out, secretly create the richest farmland on Earth? And in what surprising and wonderful ways do they keep reshaping the face of our planet every single day? The inspiring, hopeful final chapter of this story is waiting for you in part 4. After the road dies down and the ash finally settles across the land, can something truly beautiful and full of life actually rise from the ashes? How do volcanoes, known everywhere for destruction and danger, actually create the richest, most fertile farmland on Earth that feeds millions? And in what astonishing and powerful ways do they continue reshaping the face of our planet every single day, building new islands and changing continents? They end the hopeful, life-giving final chapter of the volcano story, and it might just be the most important part of all. Volcanic ash and fresh lava flows are backed with nature's best natural fertile potassium, phosphorus, magnesium, calcium, and dozens of other essential minerals that plants love. Rain and weather slowly break the rock down over time in a natural process scientists call weathering, turning the minerals into perfect plant food. The result is something special called andesite soil, one of the most fertile and productive soils in the entire world. It holds water perfectly without getting water lost. Drains beautifully so roots don't drown and stays rich and full of nutrients for thousands of years. Farmers all over the world know the secret. In Indonesia, Japan, the Philippines, and Hawaii, they grow iced tea, coffee, and delicious fruit on the volcanic source year after year. Right here in Vietnam's Central Highlands, the ancient paste flows from our volcanoes created the famous red earth that now supports over 600,000 hectares of world-class coffee plantations. Places like Chudanja gave farmers the incredible long-lasting gift millions of years ago, and it still brings job, income, and delicious coffee to tables around the world every single day. But volcanoes don't stop at just making better soil. They actually build brand new land right before our eyes. In Hawaii, clean rivers of lava rid the ocean and create fresh new coastline every single year. Adding acts of new territory to the islands, Ireland has gained entire new peninsulas and land areas from recent eruptions that people can now walk on. The tiny island of Surtsey appeared suddenly off the coast of islands in 1963 from a submarine eruption and has already become a complete thriving ecosystem filled with plants, birds, insects, and even small animals. A living natural science laboratory that scientists study to understand how life colonized new land. On a much bigger planetary scale, volcanoes play a huge role in building entire continents, opening new oceans and driving the alert slowdowns of tectonic plates over millions of years. Ancient super eruptions released enormous amounts of gases that have shaped Earth's early atmosphere and made life itself possible on our planet. Even today, volcanoes influence global climate in surprising ways by shooting sulfur aerosols high into the sky, where they reflect sunlight and cool the planet naturally for a few days at a time.